Hello, happy Friday. I hope that you had a good day off yesterday and we can get started on today's information. I didn't really discuss in detail on Wednesday what was expected for Moodle. You need to watch this PowerPoint and then turn in your worksheet on Piecewise graphs that I already gave you. Then also to note, we have an RFC test on Monday, and then you're going to go ahead and get the next worksheet to do Monday evening. Today's PowerPoint will go over that material for that graph analysis 1 worksheet that's going to be due on Tuesday. Then we're going to go ahead and we'll be 1 day behind on that original worksheet that I gave you. So graph analysis 2 and 3 are Wednesday things. Also test corrections are going to be due Wednesday. Then your RFC sheet 2 is due on Thursday. And we'll go ahead and have our graph analysis 5 and 6 we'll do Thursday. Those quizzes that you just took, I'll have them back to you on Monday, and the corrections will be due Friday. Friday is a half day, and it's our type 1 diabetes day. You will have an assignment for Moodle on the following Monday. Okay, so let's get started on piecewise functions. We went over them briefly on Wednesday, but it was rushed and a little bit confusing. So piecewise function is a function with different equations that have different domains. Remember, domain is the x values. And so we have some examples of what a piecewise looks like. It says f of x is equal to, and then you have this function here, and the domain is here if x is greater than or equal to 2, and the domain for this one is different, and it's for x less than 2. Usually in a piecewise function, these domains do not overlap. Okay, there's another example. You could have 3, you could have 15, it doesn't matter, but you can see here, what's interesting about this is this has a shorter interval, and then this goes to infinity, negative infinity, and this goes to positive infinity. So it still encompasses all the values from negative infinity to infinity. Okay, so piecewise, it's just like it says, it's pieces. There's 2 pieces. The easiest way to graph a piecewise function is to go ahead and evaluate each of the different functions at different points on each interval. So you can see here we have f of 1 is equal to, because we know what our domain is, we know that when x is less than 2, it's this function, so we plug it in to the function 2x, and we have 2 times 1, and we get f of 1 is equal to 2, and we now have an ordered pair that we can graph. We can repeat this with other points, and we see that this one, for f of 3, this is in this domain right here, because x is greater than or equal to 2, so 3 is greater than or equal to 2, so we use the x plus 2 function, and we have 3 plus 2, and we get 5, and again we have an ordered pair. Obviously 2 points is not sufficient, so you would go ahead and graph a few more points. Also, to note, you look at your x-intercepts. Remember, an x-intercept is when y is equal to 0. So we do this for both functions. So we have 0 for our y equals x plus 2, and we go ahead and plug in 0 and solve for x. When we solve for x, we get x is equal to negative 2. We do this for the other function as well. But when we look at these closer, right, this x-intercept, this is when x is negative 2. But negative 2 is not part of this domain up here. So it's not part of this function, and this is not actually an intercept of the graph. But this is 0, 0 using that function, because we found that x is equal to 0, which is the 2x function. And we do the same thing for our y-intercepts. Y-intercepts are when x is equal to 0, and you can see that you're going to get, with both functions, you end up getting the same point of 0, 0. So now we're going to go ahead and use the points that we found to graph our function. So we can go ahead and we have our graph, and I'm gonna look here, right? So the big point is that x is 2, almost like an asymptote. And we have when x is greater than or equal to 2, we're going to be using this function. So that's a closed dot here, right? So at 2, 4, it's a closed dot. Where for this function, it's also 2, 4, but it's an open dot. Okay? So that's why you can tell that they don't overlap. So that first one, if we draw a dotted line here, that represents our function, but it's only for x is greater than or equal to 2, so we only draw a solid line up above here. And then the same thing for x less than 2, we have this line here that goes all the way, but we're only going to color it in or make it solid for less than 2. And there you have your piecewise graph. So we can look at this graph and we can determine the domain, the range. Domain, you can see it continues on forever. So the domain is negative infinity to infinity. And then our range also is from negative infinity to infinity. And then lastly, we ask the question, is it continuous? Because part of the functions was equal to and the other was open, it still created a continuous, unbroken. So yes, this is a continuous function. All right, so let's look at a more complicated example. Again, these are all linear functions, so you can do the same thing. We have all these values, and I'm just going to click through them rather quickly so you get the idea that we're going to plug these values in, and we're going to get our points, and we're going to use them in all of our, at least have 1 or 2 points in each of our ranges x. Okay, so these were all of our points here. This was for the first function, right? You see the 1 and the 1. In our second function, we have these points, and then lastly, our third function, we have these points. And we're going to go ahead and graph this function very similar to what we did last time. Remember, we're looking at, first we're going to look at this piece at -2. And then we'll go on to positive 3 to look at it as well. So I drew my first one of x is less than, or 3x plus 2. Remember, 2 is my intercept. My slope is up 3. 1, 2, 3 over 1. And I'm drawing it as a dotted line, and then I'll color it in as a solid line for less than -2. So it will be this last piece down at the bottom. There you go. And I have an open dot here because this is an open interval. And then we continue on, and I do my next part, 2x. Same thing, connect it, but because it's between these 2 points, I do it solid in between. And then lastly, I do my -2x plus 6. I draw that graph, and then I only, even though it intersects over here, I'm only going to be drawing down here. And I draw down below, and it's open. So you see there is no overlapping, but there's a closed here and it's open here. You can't have both closed, or then it would not be a function. We're going to discuss functions in a moment. Okay, so this is a function. It's a piecewise function. There is no overlapping. And our domain, like the last one, is negative infinity to infinity. And the range is also negative infinity to 6. And the reason we can say 6, because you see here, the graph will never go above 6. But down here, this is going on continuously to negative infinity. So the next question, is it continuous? No, it's not continuous because there's a big hole here. It's a big jump, so it's not continuous. and because there's a piece or broken at x equals 3. There are piecewise functions that have more than one portion or location in which they're discontinuous. All right, lastly, let's look at some of our curves. I'm going to do this one rather quickly as well, but now we're looking at a quadratic. We know quadratic is a parabola. We do the same thing that we did before. We plug in our points, and we get all of our values. We're using points on both intervals, right? So 1 was in my lower interval here. 3 is in my upper interval. I'm going to go ahead and evaluate at 2. But because I know 2, this is equal to 2, so I use this function at 2. And I did a couple more points just to have a look at this. We graph our points. We know that we have a parabola. So at -2, it's 4. 1, 2, 3, 4. And then at -1, it's 1. We have 0, 0. We have 1, 1, 2, 4, and 3, 5. But if you look back at our function, we had for equal to 2, we had here. And this was instead a curve that we went around. You got to use your parabola, and you stop here. And then here we go on to have a straight line. Okay? So you can have a piecewise with the curve. Sometimes it may jump up and you'll have some discontinuity. Here this one did not. Okay? So now let's look at functions. A function is a relation as a set of ordered pairs. So I have here the ordered pairs. The domain is all the x values in our ordered pairs. So 0, 1, 1, 4, and 4. We don't need to list points twice. We just list the values once. So the domain is 1, 0, 1, and 4. And then range is all of our y values. And again, if there's any repeats, we only need to list them once. So we go ahead and we have our domain and our range of a set. Okay, so we're looking at these relationships now as a table. So again, these are our x and y values. If we wanted to list them as ordered pairs, we could. Or we can just go straight from the table to list our values. And again, when we write our domain and our range as a set, we don't need to repeat any numbers that are repeated. So we have these 3 examples, and the domain is -4, 1, 2, and 3. The range 3, 4, 5, and 6. Take note that we don't go in the order of the table, we go in numerical order. So we always go from least to greatest when we list our domain and range. So here it's out of order, but I'm going to go ahead and say, okay, this is my first term, my second term, third, fourth, and fifth when it comes to my domain. And then when it comes to my range, I have first, second, third, fourth, and fifth. Again, we list them in numerical order. Take a moment to look at the last one and list it yourself. And this is what you should have gotten. And your range right here. All right. Now, a function is only where you have every x value has 1 and only one value of y. So if you have a table where there's more than one y value for the same x value, then it is not a function. So we have no repeats of x values, so yes, it is a function. But then if we look at this one, right here, we have a 1 and we have a 1, and they both have a different output, so this is not a function. And then the last one is a function. Using a graph. So graph, though, we do what's called the vertical line test. The vertical line test is if we moved a vertical line across the graph, whether it would be a function or not. If you're given a function, you can create a table of values and determine whether it is a function or not. In this case, they're both functions. Last one, look at it yourself. Determine whether it's a function or not. Pay attention to those x values and y values. Remember, for each x value, there should be one and only one output value or y value. So it's not a function. All right, now we're getting to that vertical line test I was talking about. So here's a vertical line test, and you just basically take a line and move it across your graph. So we have here a function, and if we took this line and moved it in either direction across the entire graph, would we ever hit 2 points? And in this case, no, because as we move it, we're always only hitting 1 point on the graph. You can see there, so it is a function. But if you look here and I draw my vertical line, this is one x value, and there's 2 different y values. So no, it is not a function. Okay, so vertical line test you could always use on a graph. So let's take 2x minus 3. We used it as a table before. This was our table of values, and we said it was a function. But we could also graph it. Graph it, put our vertical line on there, move it across our graph, and determine that yes, it is a function. We could do the same thing with our x squared. We had our table of values, we used that to evaluate. We could also graph it and then use the vertical line test, and yes, this also is a function. And let's go back to our last one that we had, and it was x equals y squared. We had our table of values that told us that there were 2 y outputs. But we could have graphed x equals y squared as well and gotten this. And then we could have used the vertical line test and identified that there are 2 y values, and no, it is not a function. Okay, so find the domain and range of the function using a graph. So we can just look here. Remember, domain is our x values. So we start here, which it's hard to see on this PowerPoint, but that's 1, 2, negative 3. And the graph ends here, which is at 1, 2, 3, positive 4. So our domain is negative 3 to 4. If it includes the points, then we use a bracket. If it does not include the endpoints, then we use a parentheses. So in this case, it did include both of those points, so we used a bracket. If we had seen something like this, an open circle here, you would have written it like this. And then the range is the y values, and so our range goes from here to here. Count your points and get your range. And again, because it included those 2 points, it has brackets here that says negative 4, 2. If we had had that open point, it would be negative 4 and 2. Oops, sorry, backwards. Negative 4, parentheses 2. Okay, so find the domain and range of the function here. So we can see because they have this arrows here, these are going on to infinity. So my domain is from negative infinity to infinity. And then you could also see for our range, this is an endpoint. There's no values below it. So it includes this point, so you would use a bracket for this value of -2, and it goes on to positive infinity. And you can't have a closed bracket for infinity because it's not an endpoint. And we get our range -2 infinity. All right, stick with me here. We're almost done. Function notation. We've already addressed this in RC, so I'm just going to click through and write. Right, so we see something like y equals. We usually write y of x as f of x, meaning the function at a point x. Okay, so those are all the same terminology. Just to review, this is function of x and it's read f of x. And the last little bit on function, plugging the values in. Again, we've done this quite a bit, but just to review in case you weren't sure. Okay, and remember this f of 3 is the same thing as our y value. All right. I think I have